Imagine floating in an abyss so vast, so unfathomably dark, that the light from our sun is nothing more than a particularly bright distant star. You are billions of miles from home, surrounded by a biting cold that approaches absolute zero, moving at a speed of over 38,000 miles per hour. You are completely alone. For decades, you have been falling outward, away from the warmth of the inner solar system, piercing through the invisible magnetic boundaries of our cosmic neighborhood. And then, suddenly, the deafening silence of space is broken. You detect something that shouldn't be there, a wall of superheated plasma, burning at thousands of degrees, acting as an invisible barrier separating the realm of the sun from the uncharted, chaotic ocean of interstellar space. You are Voyager, a machine built by human hands in the 1970s, carrying a golden record of a world that has aged nearly half a century since you left it. What you have just found at the absolute edge of the solar system is sending shockwaves through the scientific community back on Earth. It changes everything we thought we knew about our place in the universe. But what exactly is this wall of fire? How did a piece of vintage technology survive long enough to find it? And what terrifying, beautiful truths does this discovery reveal about the bubble that protects our fragile planet from the harsh radiation of the galaxy? If you want to understand the terrifying realities of deep space and the most audacious mission in human history, stick around. Because the data Voyager is sending back right now is rewriting the rulebook of astrophysics. To understand the sheer magnitude of what Voyager is currently experiencing out in the interstellar medium, we have to travel back to a time before we even knew what the outer solar system looked like, back to a rare celestial alignment that happens only once every 176 years, and back to a daring mission that, surprisingly, almost never happened at all. We have to understand how humanity managed to build a spacecraft that could not only survive the harshest environments imaginable, but also continue to talk to us from the space between the stars. The story of Voyager is not just a story of cold metal and circuitry. It is the story of human audacity, the relentless pursuit of knowledge, and a group of rogue engineers who decided to secretly build a machine meant for eternity. When the first concepts for what would become the Voyager mission were being sketched out on blackboards, the world was a very different place. It was the 1960s and early 70s. The space race had been fundamentally about one thing: reaching the moon before the Soviets. Once Apollo 11 achieved that goal, the public's appetite for massive space expenditures began to wane. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were little more than blurry, mysterious smudges in the lenses of our most powerful Earth-based telescopes. We knew almost nothing about them. We didn't know about the raging, eternal storms of Jupiter, or the intricate orbital mechanics of Saturn's rings. We certainly had no concept of the subsurface oceans and erupting ice volcanoes that we now understand populate those distant frozen moons. The outer solar system was a massive blank canvas waiting for someone bold enough to try and paint it. The catalyst for this monumental journey was discovered almost by accident. In the summer of 1965, an aerospace engineering intern named Gary Flandreau was working at NASA's Jet Propulsion Laboratory. His task was relatively straightforward, but mathematically exhausting. He needed to chart the orbital paths of the outer planets for the late 1970s and 1980s to see if any efficient probe trajectories existed. As Flandreau plotted the orbital tracks, a pattern began to emerge. A pattern so perfect, so incredibly rare, that it sent a jolt of electricity through the entire laboratory. Flandreau realized that in the late 1970s, Jupiter, Saturn, Uranus, and Neptune would be aligned on the exact same side of the Sun. This specific configuration, he calculated, happens exactly once every 176 years. The implications of this math were staggering. If a spacecraft were launched at precisely the right time, it could use the immense gravity of each giant planet to slingshot itself to the next one. This technique, known as a gravity assist, would essentially steal a microscopic fraction of the planet's orbital momentum and transfer it to the spacecraft. dramatically boosting its speed without requiring an ounce of extra rocket fuel. To put this into perspective, without this alignment, a standard journey to Neptune using the propulsion technology of the era would take roughly 30 years. That was an impossible time frame. No electronics could survive 30 years in the harsh radiation of deep space, and no budget committee would approve a mission that wouldn't deliver results for 3 decades. But with Flandreau's gravity assist trajectory, the trip to Neptune could be cut down to just 12 years. It was a cosmic loophole, a once-in-a-lifetime opportunity to tour the giants of our solar system in a single elegant sweeping trajectory. They enthusiastically called it the Grand Tour. The window for this Grand Tour was incredibly narrow, and the pressure was immense. NASA had to design, build, and launch a spacecraft capable of not just reaching these worlds, but surviving the journey. However, politics almost killed the dream before it began. By the early 1970s, the American economy was struggling, and the Nixon administration was severely cutting NASA's budget. The estimated cost for the Grand Tour, designing dedicated spacecraft to visit all 4 outer planets, was nearly $1 billion. Congress balked at the price tag and completely cancelled the Grand Tour program. The planetary scientists were devastated. A 176-year window was about to close, and humanity was going to miss it because of budget cuts. But the engineers at the Jet Propulsion Laboratory were not ready to give up. They proposed a radically scaled-back compromise. They called it the Mariner-Jupiter-Saturn 1977 project. It would cost only a fraction of the Grand Tour, at around $360 million. Officially, the mission was only funded and guaranteed to visit Jupiter and Saturn. It was pitched as a short, focused 5-year mission. Congress approved it. But behind closed doors, the engineers did something incredibly rebellious. They knew the planetary alignment was still there. They knew that if the spacecraft survived Saturn, the laws of physics would naturally allow it to continue to Uranus and Neptune. So, they quietly, meticulously over-engineered the probes. They built them not for a 5-year mission to Saturn, but for a decades-long journey to the very edge of the Sun's domain. They gave the mission a new, more inspiring name, Voyager. The engineering challenges they faced in secretly building these robust machines were monumental. Space is an environment that actively wants to destroy anything you put into it. The spacecraft would have to endure the violent, shaking vibrations of a Titan Centaur rocket launch, the extreme vacuum and freezing temperatures of deep space, and perhaps most terrifyingly, the intense radiation belts surrounding Jupiter. Jupiter's magnetic field is a monster, trapping charged particles and accelerating them to near the speed of light. It is a radiation environment strong enough to fry the electronics of any unshielded probe within hours. To survive this, the engineers had to essentially build an autonomous robot that could think for itself. Because radio signals, travelling at the speed of light, would take hours to cross the vast distances between Earth and the spacecraft, ground control couldn't joystick the probe in real time. If an emergency happened, by the time the warning signal reached Earth and a command was sent back, the spacecraft would be dead. The Voyagers had to be smart. They were equipped with some of the most advanced computers of the time. Now, by today's standards, they are almost comically primitive. The total memory capacity of a Voyager spacecraft is less than 70 kilobytes. That is roughly equivalent to a modern electronic car key, or a fraction of a single low-resolution photo on your smartphone. They didn't even have solid-state hard drives. They recorded their data on digital 8-track tape recorders. Yet, those primitive computers were designed with brilliant redundant systems. They were capable of identifying a fault, shutting down a broken component, and switching to a backup without any human intervention. This robust, self-healing architecture is the primary reason why these machines are still functioning today, almost half a century later. But perhaps the most brilliant and necessary engineering feat was the power source. Beyond the orbit of Mars, the light from the Sun becomes exponentially weaker. Solar panels are entirely useless in the outer solar system. A spacecraft heading to Jupiter and beyond is flying into perpetual twilight. and eventually, deep darkness. To survive, the Voyagers needed a heart that beat with nuclear heat. They were equipped with radioisotope thermoelectric generators, or RTGs. These devices are not nuclear reactors. They don't use fission. Instead, they contain pellets of an unstable isotope, plutonium-238. As the plutonium naturally decays over decades, it generates immense, glowing heat. Clever devices called thermocouples then convert this heat directly into electricity. This steady, reliable flow of power is what kept the spacecraft's scientific instruments alive, what kept its computers thinking, and what keeps its faint radio transmitters beaming data back across the void today. It is a slow, dying nuclear fire, one that loses a little bit of its strength every single year as the plutonium depletes, but it has proven to be the most resilient power source ever sent into the cosmos. As the physical machines were being meticulously constructed in the sterile clean rooms of JPL, another profound project was taking shape alongside them. A project not about engineering, thrust, or radiation shielding, but about philosophy, art, and the very essence of what it means to be human. The renowned astronomer Carl Sagan was tasked with creating a message to accompany the spacecraft. He and his committee understood a profound truth about the Voyager trajectories. By using the gravity of Jupiter and Saturn to accelerate, the probes would be moving so fast that they would achieve escape velocity from the Sun itself. They were on a one-way trip. They would never come home. They would eventually drift out of the solar system entirely and become humanity's first true interstellar emissaries. Sagan knew that the chances of these silent probes ever being intercepted by an advanced alien civilization were astronomically small, effectively zero. Space is simply too vast and the probes are too small. But the symbolic value of sending a message in a bottle out into the dark cosmic ocean was undeniable. It was a statement of our existence. The result of this philosophical endeavour was the Golden Record. This phonograph record, made of gold-plated copper to resist the slow degradation of deep space, is perhaps the most romantic and deeply moving object ever constructed by human hands. It is a time capsule, a carefully curated emotional snapshot of Earth and its inhabitants, designed to last for over 1 billion years in the pristine vacuum of space. The record contains spoken greetings in 55 different Earth languages, spanning from ancient Akkadian and Sumerian to modern dialects. It contains an intricate audio landscape of our world, the sound of wind whistling through trees, the heavy crash of ocean waves, the calls of wild whales and singing birds, the rhythmic heartbeat of a mother, and the quiet, intimate sound of a human kiss. It also contains an hour and a half of carefully selected music, representing the diverse, vibrant cultural tapestry of humanity. There is the mathematical precision of Bach and Beethoven, traditional rhythmic music from Senegal and Peru, complex Javanese gamelan, and the soulful, hauntingly beautiful blues of Blind Willie Johnson's track. Dark was the night, cold was the ground. Johnson's song, a wordless moaning guitar piece expressing profound, desperate loneliness and human sorrow, was explicitly included because Sagan's committee felt strongly that a message to the cosmos shouldn't just be a highlight reel of our scientific triumphs. It had to be honest. It had to represent our struggles, our vulnerability, and the deep, universal emotional resonance of the human experience. Along with the audio tracks, the record contains analog encoding of 115 images. If an alien intelligence figures out how to decode them, they will see diagrams of our solar system, basic illustrations of human anatomy and reproduction, pictures of children playing, vast landscapes, bustling cities, and diverse animals. It is a comprehensive, beautiful, and profoundly touching summary of who we were at the exact moment those probes left our atmosphere. The instructions for playing the record and the precise location of our Sun relative to 14 rapidly spinning pulsars are etched directly onto the aluminum cover. It is a cosmic map, a beacon leading back to a tiny, insignificant blue dot. When the time finally came to leave Earth, the drama was far from over. Voyager 2 was actually launched first on August 20th, 1977. Voyager 1 would follow a few weeks later on a faster, shorter trajectory. But as Voyager 2 sat atop its massive Titan Centaur rocket, roaring into the Florida sky, things immediately went wrong. The violent shaking of the launch caused the spacecraft's internal gyroscopes to wildly fluctuate. The primitive 70-kilobyte computer became confused. It thought the spacecraft was failing. In what engineers later jokingly called a mutiny, the computer started autonomously shutting down primary systems and frantically switching to backups while still hurtling through the atmosphere. Ground control watched in absolute terror as their multi-million-dollar probe seemed to be dying before it even reached orbit. Through frantic, brilliant troubleshooting, the engineers managed to send commands to calm the computer down, essentially telling it to ignore the chaotic sensory input of the launch and trust that it was on the right path. It was a terrifying reminder of how fragile this endeavour was. Weeks later, Voyager 1 launched flawlessly. Because Voyager 1 was placed on a faster trajectory, it would actually overtake Voyager 2 and arrive at Jupiter first. Its mission prioritized a dangerously close flyby of Saturn's largest moon, Titan, rather than the continuation of the Grand Tour. Titan was known to possess a thick, mysterious atmosphere, an extreme rarity for a moon, and scientists were desperate to see what chemical secrets lay hidden beneath its opaque orange clouds. This specific targeting decision meant that Voyager 1's path would ultimately be bent sharply upward by Titan's gravity, flinging it out of the flat planetary plane of the solar system entirely. Voyager 2, however, was tasked with the full ambitious Grand Tour, targeting Jupiter, Saturn, and then relying on successful pinpoint gravity assists to push it onward into the dark abyss toward Uranus and Neptune. The energy and excitement of those launches marked the beginning of a true golden age of planetary exploration, as the two heavily shielded spacecraft cleared the Earth's orbit and ventured outward into the rocky expanse of the asteroid belt. They were performing beautifully. They were heading into the dark unknown, carrying our finest science, our most beautiful sounds, and our deepest hopes. For the stressed engineers back at JPL, the real test of patience was just beginning. The sheer incomprehensible scale of the distances involved meant that the mission required years of waiting. It would take a year and a half just to reach Jupiter, the very first stop on this epic journey. During that long, quiet cruise phase, the probes operated in the silent emptiness of interplanetary space. Their instruments occasionally tested the solar wind. Their primitive tape recorders whirred, and their cameras were calibrated, staring out into the black, waiting for the giant to appear. No one, not even the most visionary and optimistic scientists on the project, could have possibly predicted the sheer volume of paradigm-shifting, terrifying discoveries that awaited them in the dark. They thought they were sending simple cameras to take black and white pictures of dead, heavily cratered rocks. They had absolutely no idea that they were about to uncover dynamic, chaotic worlds, bursting with violent volcanic activity, incredibly complex atmospheric dynamics, and bizarre magnetic mysteries that would force them to rewrite every textbook on planetary science. And since the Voyagers were about to brutally open our eyes to the true violent nature of our solar neighbourhood, and in doing so, they would quietly prepare us for the ultimate shock that lay waiting for them decades later, at the very invisible boundary of the sun's domain. The cosmic stage was set. The 176-year alignment was perfect, and the machines were functioning. The curtain was about to rise on the greatest, most profound journey of exploration in human history. As Voyager 1 and Voyager 2 crossed the invisible threshold of the asteroid belt, they were leaving the warm, familiar inner solar system behind forever. The sun, which dominates our earthly sky as a blinding sphere of life-giving heat, was steadily shrinking in their rearview cameras, reducing itself to nothing more than an exceptionally bright cold star in a sea of absolute black. Ahead of them lay a monster. For months during the approach, Jupiter grew from a pale, steady point of light into a massive, swirling orb that completely dominated the spacecraft's field of view. But Jupiter is not merely a planet in the way we understand Earth or Mars, no. It is a failed star, a gargantuan sphere of hydrogen and helium so massive that it generates its own internal heat. radiating more energy out into space than it receives from the distant sun. And as the Voyagers hurtled closer at tens of thousands of miles per hour, they were about to plunge straight into the most hazardous environment in the entire solar system. Before Voyager, our understanding of Jupiter was frustratingly basic. Earth-based telescopes, peering through the turbulent blur of our own atmosphere, could only resolve blurry horizontal stripes of orange and white, along with the famous Great Red Spot. We knew it was a gas giant, but we had absolutely no conception of the terrifying, violent fluid dynamics operating beneath those upper clouds. The anticipation at the Jet Propulsion Laboratory was agonizing. Because of the vast distance, radio signals carrying the first close-up images took nearly 40 minutes to travel from the spacecraft to the giant dish antennas back on Earth. The scientists and engineers huddled around primitive, flickering cathode ray tube monitors, waiting as the images rendered line by excruciating line. What slowly materialized on those screens sent shockwaves through the scientific community. They were not looking at a static, hazy ball of gas. They were looking at a turbulent, chaotic atmosphere of unimaginable violence. The cloud bands of Jupiter were revealed to be raging jet streams, moving in opposite directions at hundreds of miles per hour, creating massive, swirling eddies and complex storm systems at their boundaries. The Great Red Spot, a storm that humanity had been observing for over 300 years, was finally seen in terrifying detail. It was a massive, high-pressure anticyclone large enough to swallow the Earth 2 or 3 times over, its edges churning and cannibalizing smaller, neighboring storms to sustain its eternal wrath. The Voyagers captured lightning strikes illuminating the dark side of the planet, superbolts thousands of times more powerful than anything ever recorded on Earth. They discovered that Jupiter actually has a faint system of dark, dusty rings, completely invisible from our vantage point. But as awe-inspiring as the atmosphere was, the true revelation, the paradigm-shifting discovery that completely rewrote the rulebook of planetary science, did not come from the giant planet itself. It came from its moons. Prior to 1979, planetary science operated under a very strict, logical assumption. The general consensus was that the further you travel from the heat of the sun, the colder and more dead the worlds become. Moons, in particular, were thought to be nothing more than geologically inactive, frozen rocks heavily scarred by billions of years of asteroid impacts, much like our own moon. They were expected to be silent, static, and profoundly boring. The Voyagers were about to shatter that assumption into a million pieces. As the spacecraft targeted the 4 large Galilean moons, Callisto, Ganymede, Europa, and Io, the incoming data made absolutely no sense. The closest large moon to Jupiter is Io. When the first colour images of Io appeared on the monitors at JPL, scientists were utterly baffled. It didn't look like a moon. It looked like a diseased pizza. It was covered in vibrant shades of sulphurous yellow, bright orange, stark white, and deep black. Even stranger, there was an absolute lack of impact craters. In a solar system where every solid body is peppered with the scars of ancient collisions, Io's surface was impossibly smooth and fresh. The mystery was violently solved a few days later by a navigation engineer named Linda Morabito. While examining an overexposed image of Io taken to help calculate the spacecraft's exact position, she noticed a strange, faint, umbrella-shaped anomaly rising off the edge of the moon against the blackness of space. It wasn't an artifact of the camera. It was a massive plume of material erupting nearly 200 miles into space. Voyager had just discovered active volcanism on another world. This was an absolute earthquake in the scientific community. How could a tiny moon sitting in the freezing depths of the outer solar system, hundreds of millions of miles from the sun, possess enough internal heat to melt rock and power massive volcanoes? The answer lay in a terrifying invisible force called tidal heating. Io is caught in a relentless, brutal gravitational tug-of-war. On one side is the immense crushing gravity of Jupiter. On the other side is the rhythmic, repeating gravitational pull from the outer moons, Europa and Ganymede. As Io orbits, these competing forces literally stretch and squeeze the solid rock of the moon, much like you might rapidly bend a piece of metal back and forth until it becomes hot to the touch. The immense friction generated by this gravitational kneading melts the interior of the moon, creating a subsurface ocean of magma. Io is a world turning itself inside out, constantly repaving its surface with fresh lava, making it the most volcanically active body in the entire solar system. If the hellscape of Io was a shock, the next moon, Europa, presented a mystery that fundamentally altered our search for life in the universe. Where Io was a world of fire and sulfur, Europa was a world of ice. Its surface was dazzlingly bright, crisscrossed by thousands of dark, intersecting lines, making it look like a cracked eggshell. Like Io, it lacked deep impact craters, indicating that its surface was incredibly young and constantly reshaping itself. But the ice on Europa wasn't solid all the way through. The magnetic data and the specific patterns of the surface fractures told a staggering story. The ice crust was floating. The tidal friction that was melting rock on Io was operating at a slightly lower intensity on Europa, generating just enough heat to melt the ice beneath the frozen crust. Voyager provided the very first compelling evidence that Europa harbours a massive, hidden, global ocean of liquid salt water beneath its icy shell, an ocean that is likely deeper than any ocean on Earth, containing more than twice the amount of liquid water found on our entire planet. This single realization instantly shifted the entire paradigm of astrobiology. Suddenly, the habitable zone, that narrow band around a star where liquid water can exist on the surface of a planet, was no longer the only place to look for life. If you have liquid water, a source of chemical nutrients and internal heat, you have the fundamental ingredients for biology, entirely independent of the sun's warmth. Because of the primitive cameras on Voyager, Europa transformed from a forgotten dot in the telescope to one of the most vital, promising targets in the search for extraterrestrial intelligence. Navigating this treasure trove of moons was not without immense risk. To get these unprecedented close-ups, the Voyagers had to dive deep into the heart of Jupiter's magnetic field. This field is a monstrous, invisible bubble of radiation millions of miles wide. It traps charged particles from the solar wind and from Io's volcanic eruptions, accelerating them to near the speed of light. The spacecraft were subjected to a barrage of radiation, equivalent to standing a few feet from a detonating nuclear weapon. The primitive computers were heavily shielded, but the radiation still managed to flip digital bits, causing temporary glitches and corruptions in the data stream. The engineers watched nervously, knowing that a single unlucky high-energy particle could fry the central processor and instantly kill the mission. But the robust, redundant engineering of the 1970s held firm. The spacecraft survived the radiation bath, and more importantly, they stole exactly what they came for. By plunging deep into Jupiter's gravity well and flying behind the planet, both Voyagers executed a flawless gravity assist. They essentially tethered themselves to the orbital momentum of the largest planet in the solar system, drastically accelerating their speed and radically altering their trajectories, slingshotting themselves outward into the deeper dark. The next target was the jewel of the solar system, a world of intricate beauty and enduring mystery, Saturn. It would take over a year of silent, lonely cruising across the vast, empty gulf between the two giant planets before the cameras would open their eyes again. When Saturn finally swelled into view in late 1980, it presented a vision of cosmic elegance that left scientists breathless. While Jupiter was a chaotic, bruised brawler of a planet, Saturn appeared almost serene, painted in muted tones of butterscotch and pale gold. But this serene appearance was a complete illusion. Voyager's instruments quickly determined that the winds on Saturn are far more violent than those on Jupiter, howling at the equator at an incomprehensible 1,100 miles per hour. The planet is simply shrouded in a thicker layer of high-altitude haze, hiding the monstrous, raging storms churning beneath. But the true prize of the Saturn encounter was, without question, the rings. Before Voyager, telescopes showed Saturn's rings as 3 or 4 broad, solid-looking bands separated by distinct, empty gaps. There was a genuine debate among astronomers about whether they were solid sheets of material or made of individual particles. Voyager shattered those simple models forever. As the spacecraft approached, the cameras revealed that the broad bands were actually made up of thousands upon thousands of individual, razor-thin ringlets, creating a structure of mind-boggling complexity that looked like the grooves on a phonograph record. These rings are not solid. They are an impossibly vast, chaotic demolition derby composed of billions of pieces of water ice, ranging in size from microscopic dust grains to massive, tumbling mountains the size of skyscrapers. This entire structure, spanning hundreds of thousands of miles across, is incredibly thin, in some places no thicker than a few dozen yards. Voyager captured phenomena within the rings that defied immediate explanation. They saw dark, ghostly spokes forming and dissipating within hours. Structures we now believe are electrically charged dust particles levitating above the main ring plane. They discovered tiny, heavily cratered moons buried deep within the ring system. These shepherd moons, as they came to be called, act like gravitational sheepdogs. Their tiny gravitational pulls clear out the gaps in the rings and keep the icy debris contained in sharp, distinct edges, preventing the entire system from slowly drifting apart into space. As spectacular as the rings were, the Saturn encounter forced a brutal, heartbreaking decision upon the mission planners. A decision that would permanently separate the destinies of the two twin spacecraft. The priority target for the entire Saturn system was not the rings, nor the planet itself. It was Saturn's largest moon, Titan. For decades, astronomers knew that Titan was unique. It was the only moon in the solar system known to possess a substantial atmosphere. In fact, its atmosphere is denser than Earth's. Scientists were desperate to see what lay hidden beneath its thick, opaque orange haze. There was a genuine, tantalizing possibility that Titan could harbour liquid oceans of methane and complex, prebiotic chemistry, essentially a frozen snapshot of what the Earth might have looked like billions of years ago before life began. Because Voyager 1 had arrived at Jupiter first, and was on a faster trajectory, it was chosen to make the sacrificial dive toward Titan, to get close enough for its instruments to sniff the atmosphere and attempt to peer through the smog. Voyager 1 had to fly incredibly close to the moon's south pole. The spacecraft performed beautifully, skimming the edge of the hazy atmosphere. It confirmed that Titan's air is composed primarily of nitrogen, just like Earth's, laced with complex hydrocarbon smog. It was a massive scientific victory, proving that organic chemistry was occurring naturally in the deep freeze of the outer solar system. But this invaluable data came at a massive permanent cost. The laws of orbital mechanics are unforgiving. By passing so close to Titan, Voyager 1 used the moon's gravity to drastically alter its course. But instead of being slung forward to the next planet, the flyby sharply bent Voyager 1's trajectory upward, throwing it completely out of the flat, ecliptic plane of the solar system where the rest of the planets reside. There would be no more planets for Voyager 1. Its grand tour was officially over. It was now heading upward and outward, climbing away from the planetary disk at over 38,000 miles per hour, destined to plunge straight into the dark void of interstellar space. This left Voyager 2 as the sole remaining hope for exploring the rest of the solar system. The engineers at JPL breathed a collective sigh of relief as Voyager 2 successfully navigated its own perilous path through the Saturnian system, executing a perfect gravity assist without committing to a Titan flyby. Voyager 2 was now officially on an extended mission, a lone scout hurled into an abyss so deep that the light of the sun would soon become indistinguishable from the background stars. It was heading toward the ice giants, Uranus and Neptune, worlds so distant and dark that humanity knew practically nothing about them. The true endurance test of the machines, and the men and women who built them, was about to begin. As Voyager 2 left the Saturnian system behind, it was venturing into a region of space so remote and so incredibly dark that the very concept of planetary exploration had to be completely reinvented. The gap between Saturn and Uranus is massive. It is a vast, empty expanse of nothingness that would take the spacecraft nearly 5 long years to cross. During this silent cruise, the engineers back at the Jet Propulsion Laboratory faced a terrifying reality. Voyager 2 was flying into a zone where the sunlight is 400 times weaker than it is here on Earth. Taking a clear, high-resolution photograph at those extreme light levels while moving at tens of thousands of miles per hour is mathematically equivalent to trying to photograph a speeding bullet in a pitch-black room using only a cheap camera with the shutter left wide open. The resulting image should have been nothing but a meaningless, blurry smear, but the engineers were not about to let a billion-mile journey end in blurry photographs. Over the course of those 5 years, they essentially performed a complete, long-distance brain transplant on the spacecraft. Using radio signals that now took hours to reach the probe, they fundamentally reprogrammed Voyager 2's ancient 70-kilobyte computers. They taught the primitive machine entirely new ways to compress and transmit data. But their most brilliant hack was a technique called image motion compensation. To prevent the camera from blurring the dark, low-light images, the engineers programmed the entire spacecraft to physically rotate backward at the exact same speed that it was flying forward, keeping the camera lens perfectly locked onto its target while the shutter remained open for extended periods. To do this, they had to command Voyager to fire its tiny maneuvering thrusters for microscopic fractions of a second. It was a choreography of mind-bending precision, executed perfectly by a machine built in the 1970s, operating nearly 2 billion miles from its creators. When Voyager 2 finally arrived at Uranus in January of 1986, the revitalized machine opened its eyes to a world that was profoundly, almost disturbingly weird. Uranus is the anomaly of the solar system. Every other planet spins roughly upright like a top, but Uranus is not completely on its side. Its equator is at nearly a right angle to its orbit, meaning it essentially rolls around the Sun like a barrel. Scientists believe that billions of years ago, during the chaotic, violent early days of the solar system, an Earth-sized protoplanet smashed into Uranus with unimaginable force, permanently knocking the giant ice world off its axis. Because of this extreme tilt, the seasons on Uranus are absolute nightmares. The North Pole points directly at the Sun for 42 years of continuous, albeit weak, daylight, while the South Pole is plunged into 4 decades of freezing, absolute blackness. At first glance, the images sent back to Earth were incredibly disappointing. Instead of the vibrant, swirling storms of Jupiter or the elegant bands of Saturn, Uranus appeared as a featureless, pale blue-green billiard ball. The atmosphere, rich in methane which absorbs red light and reflects blue, seemed entirely stagnant. But the true chaos of Uranus was completely invisible to the human eye. When Voyager's instruments probed the planet's magnetic field, the data they received was so bizarre that the scientists initially thought the instruments had broken. The magnetic field of Uranus doesn't originate from its core, and it doesn't line up with the planet's rotation. Instead, it is wildly off-center, shifted away from the core by a third of the planet's radius, and it is violently tilted at a 59-degree angle. Because the planet is spinning on its side, while this off-center magnetic field rotates with it, Uranus drags its magnetosphere behind it in a massive, twisting, invisible corkscrew millions of miles long. It is a chaotic, tangled mess of magnetic energy that defies all conventional models of planetary physics. But while the planet itself hid its secrets beneath a bland blue veil, its moons provided more than enough visual shock. Uranus has a collection of small icy moons, but one in particular, named Miranda, left the geology team entirely speechless. Miranda looks like a cosmic jigsaw puzzle that was smashed to pieces with a hammer and then hastily glued back together by someone who didn't have the picture on the box. It features massive, heavily cratered plains existing right next to incredibly bizarre, grooved terrains that look like massive racetracks. But Miranda's defining feature is a sheer, terrifying drop known as Verona Rupes. It is an ice cliff that plunges straight down for an estimated 12 miles. It is the tallest known cliff in the entire solar system. To put that into perspective, if you were to somehow jump off the edge of Verona Rupes, the gravity on Miranda is so incredibly weak that it would take you a full 12 minutes of terrifying, silent freefall before you finally hit the bottom. The successful encounter with Uranus was a massive triumph, but there was no time to celebrate. The planetary alignment was pulling Voyager 2 ever outward, toward the final stop on its grand tour. Neptune. It would take another 3.5 years of travelling through the frozen dark to reach the 8th and final planet. By the summer of 1989, Voyager 2 was nearly 3 billion miles from Earth. The sunlight out here is practically non-existent, 900 times fainter than on a sunny day in Los Angeles. The heat from the probe's decaying nuclear battery was dropping, and the engineers had to start making difficult choices, systematically turning off non-essential heaters and instruments just to keep the primary systems from freezing to death. The spacecraft was tired, aging, and shivering in the dark, but it had one last performance to deliver. When the blue sphere of Neptune finally materialized on the monitors at JPL, it completely destroyed the assumption that distance from the Sun equals a dead, inactive world. Despite receiving almost zero solar energy, Neptune is a world of absolute raging violence. Its atmosphere is a deep, striking cobalt blue, much darker and richer than Uranus, and unlike its bland neighbour, Neptune was scarred by weather. Voyager captured a massive, swirling storm system perfectly scaled to Jupiter's Great Red Spot. They called it the Great Dark Spot, a high-pressure anticyclone the size of Earth, tearing through the atmosphere. Nearby, a fast-moving, bright white cloud of methane ice, nicknamed the Scooter, raced around the planet every 16 hours. But the most terrifying aspect of Neptune was the wind. As scientists tracked the movement of the clouds, their calculations yielded impossible numbers. The winds on Neptune are the fastest in the entire solar system, screaming through the frozen upper atmosphere at an incomprehensible 1,200 miles per hour. That is nearly twice the speed of sound on Earth. It is a supersonic hurricane that never ends. The discovery of such violent weather so far from the Sun presented a massive paradox. Weather is driven by heat. So where was the heat coming from? The answer is that Neptune, unlike Uranus, somehow held onto a massive reservoir of primordial heat from its formation. It radiates more than twice as much energy back into space as it receives from the distant Sun, fueling these supersonic storms from the inside out. The grand finale of the planetary encounters was an audacious dive toward Neptune's largest moon, Triton. Triton is a rogue. Every other large moon in the solar system orbits its parent planet in the same direction that the planet spins, but Triton orbits backward. This retrograde orbit is a massive red flag. It means Triton did not form from the same disk of debris that created Neptune. Instead, Triton is an intruder. It is a dwarf planet, a world born in the deep, icy expanse of the Kuiper Belt that wandered too close to Neptune millions of years ago and was violently captured by its gravity. The immense tidal forces generated during this brutal capture would have melted Triton's interior, creating a dynamic, chaotic history. As Voyager skimmed just a few thousand miles above Triton's surface, the cameras revealed a bizarre, frozen wasteland. The moon is covered in a weird, dimpled terrain that looks exactly like the skin of a cantaloupe melon. But the true shock came when scientists scrutinized the bright southern polar cap. Against the blinding white surface of frozen nitrogen, they spotted dark, smoky streaks. These weren't impact craters or shadows, they were active cryovolcanoes. Deep beneath the crust, pockets of liquid nitrogen were being heated, turning into pressurized gas, and violently bursting through the ice, shooting dark dust and frozen nitrogen plumes 5 miles up into Triton's thin atmosphere, where the supersonic winds immediately caught the material and smeared it across the landscape. The solar system was not the dead, static place we had imagined. From the sulphurous fires of Io to the freezing nitrogen geysers of Triton, Voyager proved that the cosmos is alive, dynamic and aggressively churning. With the Triton flyby complete, the primary mission of the Voyagers was over. The grand tour of the planets was finished. The massive, beautiful spheres of gas and ice were now in the rearview mirror, shrinking back into the blackness. Both spacecraft were now firmly on an escape trajectory out of the solar system, moving at tens of thousands of miles per hour toward the space between the stars. But before they fully embraced the dark, there was one last, profoundly important piece of business to attend to. A project driven not by the desire for hard scientific data, but by a deep human need for perspective. For nearly 10 years, Carl Sagan, the visionary astronomer who helped create the Golden Record, had been relentlessly lobbying NASA management with a seemingly simple request. He wanted Voyager 1, which was now flying high above the ecliptic plane of the solar system, to turn its cameras around and take one final picture of Earth. From an engineering and management standpoint, this request was met with intense resistance. The cameras were never designed to be pointed back toward the inner solar system. Looking back meant pointing the sensitive optics precariously close to the blinding glare of the sun. There was a very real risk that the sunlight could permanently fry the camera sensors, blinding the spacecraft forever. Furthermore, the image would have virtually no scientific value. Earth would be nothing more than a microscopic speck. Why risk the equipment and spend precious deep space network tracking time for an unscientific photograph? But Sagan's argument was unassailable. He argued that the true value of the picture would not be scientific, but psychological and philosophical. It would force humanity to see itself not as the center of the universe, but as a fragile, tiny outpost in a vast, indifferent cosmic ocean. Finally, in early 1990, NASA relented. The commands were sent. Voyager 1, now nearly 4 billion miles away, slowly rotated its entire body, pointing its fading cameras back across the immense gulf of space it had just traversed. It took a mosaic of 60 frames capturing the Sun, Venus, Jupiter, Saturn, Uranus and Neptune. A cosmic family portrait. And there, in one of the frames, caught in the center of a scattered ray of sunlight reflecting off the camera optics, was Earth. It was less than a single pixel wide, a pale blue dot, suspended in the deep, terrifying blackness of the void. When the image was finally processed and released to the public, it triggered a massive cultural and philosophical shift. Looking at that tiny, fragile pixel, it was impossible not to feel a profound sense of unity and vulnerability. Every human being who ever lived, every king, every peasant, every war, every piece of art, every tear, and every laugh existed on that microscopic speck of dust, floating in a sunbeam. It remains, to this day, one of the most important photographs ever taken, a humbling mirror held up to human hubris. Shortly after taking the family portrait, the command was sent to permanently turn off the cameras on both Voyagers. It was a somber moment, but a necessary one. The cameras required massive amounts of power and internal heating to function, and the radioactive batteries were slowly, inevitably dying. To survive the long, uncharted journey ahead, the spacecraft had to prioritize their ears and their sense of touch over their eyes. The engineers needed to keep the particle detectors, the magnetometers, and the plasma sensors alive for as long as possible. The Voyagers were now flying blind into the longest, darkest phase of their mission. They were heading for the boundary line, the invisible edge where the protective bubble of our sun ends, and the terrifying, violent realm of interstellar space begins. For decades, the public largely forgot about the Voyagers. Without new, stunning pictures of planets to grace the covers of magazines, the mission faded into the background. But the spacecraft were not dead. They were quietly, relentlessly falling outward, covering 1 million miles every single day. And as they pushed deeper into the void, they were approaching a massive, invisible structure that scientists knew must exist, but had never actually seen or measured. It is called the heliosphere. To understand what the Voyagers were about to encounter, you have to understand that our sun is not just a source of light and gravity. It is violently active. It constantly blasts out a relentless, screaming hurricane of charged particles, plasma and magnetic fields known as the solar wind. This wind expands outward in all directions at over 1 million miles per hour, acting like a massive snowplow. As this solar wind races away from the sun, it creates a gigantic invisible bubble that envelops all the planets, the asteroid belt, and the vast expanse of the Kuiper belt. This bubble, the heliosphere, is our shield. Beyond this bubble lies the interstellar medium. This is not empty space. The space between the stars is filled with the cold, dense, and highly radioactive debris of ancient exploded supernovas. It is a chaotic, swirling ocean of high-energy cosmic rays and interstellar plasma. Without the heliosphere pushing back against this interstellar storm, life on Earth would likely be impossible, as our atmosphere would be stripped away and our planet bombarded by lethal levels of cosmic radiation. The profound mystery that haunted astrophysicists was simple. Where exactly does this bubble end? Where is the exact boundary where the solar wind finally runs out of energy and the interstellar medium takes over? No one knew. Some models predicted the boundary was just beyond Jupiter. Others thought it might be out past Neptune. As the Voyagers sailed through the 1990s and into the early 2000s, scientists watched their telemetry with agonizing anticipation. Every day, they expected to see the data spike, indicating that the spacecraft had hit the wall, but the years dragged on, and the solar wind continued to blow steady and true. The bubble was vastly larger than anyone had dared to imagine. It wasn't until the year 2004, more than 27 years after launch, that the first sign of the boundary finally arrived. And it came not with a whisper, but with a shockwave. The shockwave that hit Voyager 1 in late 2004 was the mathematical equivalent of a cosmic car crash. For nearly 3 decades, the spacecraft had been flying through a relatively smooth, uninterrupted flow of solar wind, moving outward from the Sun at over 1,000,000 miles per hour. But suddenly, the telemetry sent back to the Jet Propulsion Laboratory showed something impossible. The solar wind had violently slammed on the brakes. Its speed plummeted, its density spiked, and its temperature skyrocketed. Voyager 1 had not hit a physical wall of stone or ice, but it had collided with a massive, invisible wall of pressure. Astrophysicists call this boundary the termination shock. To visualize what the spacecraft was experiencing, imagine turning on a faucet in your kitchen sink. The water hits the bottom and spreads outward in a smooth, fast, shallow layer. But at a certain distance from the center, the water suddenly piles up, creating a turbulent, bubbling, raised ridge before flowing sluggishly down the drain. The Sun is that faucet, and the solar wind is the water. Voyager 1 had just smashed into the cosmic ridge. By crossing the termination shock, the spacecraft had entered a chaotic, transitional region known as the heliosheath. It was a bizarre, turbulent purgatory between our solar system and the deep interstellar void. The smooth, predictable physics of the inner solar system were gone. Voyager was now navigating through a frothy, churning sea of magnetic bubbles. As the Sun rotates, its magnetic field twists and folds, and out here at the absolute edge of its influence, that magnetic field begins to break apart and reconnect, forming massive cylindrical bubbles of magnetism, millions of miles wide. The spacecraft was essentially bouncing from bubble to bubble, traversing an environment that no computer model had accurately predicted. The sheer volume of data pouring into the tracking stations on Earth was overwhelming, forcing scientists to rewrite their understanding of fluid dynamics on a galactic scale. But the true shock came from the temperature readings. As Voyager pushed deeper into the heliosheath, approaching the absolute outer boundary of the Sun's influence, it detected what could only be described as a wall of fire. The instruments recorded plasma temperatures spiking to mind-bending levels, reaching anywhere from 30,000 to 50,000 degrees Fahrenheit. This is radically hotter than the actual surface of the Sun. It sounded like an apocalyptic scenario. How could an aging piece of 1970s technology, largely made of aluminum and primitive electronics, survive plunging into a 50,000-degree inferno? Why didn't Voyager instantly vaporize? The answer lies in a fascinating, deeply counterintuitive paradox of space physics. Temperature and heat are not the same thing. Temperature is simply a measurement of how fast the individual particles in a gas or plasma are moving. In the heliosheath, the particles are moving incredibly fast, violently agitated by the collision between the solar wind and the interstellar medium. Therefore, they have an extremely high temperature. But heat measures the total amount of energy transferred. Out at the edge of the solar system, space is almost a perfect vacuum. Even though the individual particles of plasma are boiling hot, they are so incredibly far apart that they almost never touch the spacecraft. There is not enough physical matter to actually transfer that thermal energy to the metal hull. So Voyager 1 was flying through a literal wall of fire, surrounded by plasma that could melt steel, while the spacecraft itself was slowly freezing to death in an environment that felt like absolute zero. It is an environment of extreme, terrifying contradictions. For 8 long years, Voyager 1 navigated this violent, bubbling purgatory. The engineers on Earth watched the data with bated breath, knowing that the ultimate boundary, the heliopause, could arrive at any moment. The heliopause is the absolute edge of the bubble. It is the theoretical line in the sand, where the outward pressure of the dying solar wind is finally permanently overpowered by the immense crushing weight of the interstellar ocean. Nobody knew exactly what crossing that line would look like. Some scientists believed it would be a gradual, blurry fading out. Others thought it might be a sharp, violent transition. In the late summer of 2012, 35 years after it launched from Florida, Voyager 1 gave humanity the answer. On August 25, 2012, the data streams radically shifted. For its entire life, Voyager's particle detectors had been registering a steady, heavy rainfall of low-energy particles originating from our Sun. On that day, the bottom completely dropped out. The number of solar particles plummeted to near zero. Simultaneously, a different set of sensors lit up like fireworks. The spacecraft was suddenly being bombarded by an intense, terrifying level of galactic cosmic rays. These are high-energy particles travelling at near the speed of light, generated by the explosive deaths of massive stars and ancient supernovas located thousands of light-years away. For 4.5 billion years, the Sun's heliosphere had protected the Earth and the inner planets from this lethal cosmic radiation. Now, Voyager had stepped outside the shield. It had pierced the bubble. It was swimming in the raw, unfiltered radiation of the Milky Way galaxy. Humanity had officially become an interstellar species. 6 years later, in late 2018, Voyager 2 repeated the feat, crossing the heliopause in a completely different location. Because Voyager 2 still had a fully functioning plasma science experiment, an instrument that had unfortunately broken on Voyager 1 back in 1980, it provided an even clearer, more detailed picture of the boundary. The transition was not a slow fade. It was a remarkably sharp, distinct wall. In the span of just a few days, the environment completely transformed. It was definitive proof that our solar system is a confined, localized bubble, floating in an incredibly hostile, highly pressurized ocean of interstellar plasma. And this interstellar ocean is not silent. It is vibrating. One of the most haunting and poetic discoveries made by the Voyagers after crossing the boundary was that the space between the stars actually has a sound. Space is a vacuum, meaning sound waves cannot travel through it in the way we hear them on Earth. But plasma waves, oscillations in the ionized gas that fills the interstellar medium, can be detected and translated into audio frequencies by Voyager's instruments. What they recorded is a continuous, eerie, low-frequency hum. It is the ambient noise of the galaxy, the distant vibration of 1,000,000 exploding stars and spinning pulsars. But occasionally, this quiet hum is violently interrupted by a massive, crashing wave. Even though Voyager 1 is firmly outside the Sun's protective bubble, it is still close enough to feel its wrath. When our Sun experiences a massive coronal mass ejection, a violent eruption that blasts billions of tons of solar material into space, that material races outward, eventually slamming into the inner wall of the heliopause. The impact is so immense that it acts like a cosmic drumstick hitting a snare drum. It sends a massive shockwave rippling outward through the dense interstellar plasma. More than a year after the Sun erupts, these shockwaves wash over the tiny distant Voyager spacecraft, registering as a rising, whistling pitch on the plasma wave instruments. It is a solar tsunami, a reminder that even in the dark, cold depths of interstellar space, the violence of our parent star can still reach out and touch us. As the science data from interstellar space continued to blow minds, A much darker, more desperate drama was unfolding back on Earth in the control rooms of the Jet Propulsion Laboratory. The Voyagers are dying. The plutonium power sources that have kept their digital hearts beating since 1977 are decaying. Every single year, both spacecraft lose about 4 watts of electrical power. They are currently operating on less than half of the power they had at launch. To put that into perspective, the entire Voyager spacecraft, including its computers, its radio transmitters, and all of its scientific instruments, is currently running on the equivalent of a standard refrigerator light bulb. Managing this rapidly vanishing power supply has become a massive, high-stakes game of long-distance survival. The engineering team has been forced to make agonizing decisions, systematically shutting down systems to conserve energy. They turned off the cameras decades ago. They have turned off redundant computer systems. But the most terrifying sacrifices have been the heaters. Deep space is unimaginably cold. The scientific instruments and the fuel lines rely on tiny electric heaters to keep them from freezing solid and cracking apart. As power levels dropped, engineers had to deliberately turn off the heaters for vital instruments like the cosmic ray subsystem and the ultraviolet spectrometer. They fully expected the intense cold to immediately kill the instruments, but defying all logic and engineering specifications, the instruments survived. Their temperatures dropped far below their designed operating limits, plunging well below -100 degrees Fahrenheit. Yet they continued to return pristine data. The machines simply refused to die. But cold wasn't the only enemy. Over 40 years in deep space takes a massive physical toll on the hardware. In 2017, engineers noticed a critical problem with Voyager 1. The primary attitude control thrusters, tiny rocket engines that emit brief, microscopic puffs of hydrazine gas to keep the spacecraft's antenna pointed directly at Earth, were wearing out. They were degrading, losing their efficiency. If the antenna drifted even a fraction of a degree away from Earth, the faint radio signal would be lost into the cosmic void, and the mission would instantly end. The engineering team needed an alternative. They looked at the spacecraft's schematics and realized there was a backup set of thrusters, called the trajectory correction maneuver thrusters. The problem was, these thrusters had not been fired since November of 1980, when Voyager 1 flew past Saturn. For 37 years, they had sat completely dormant, frozen in the vacuum of space. No one knew if they would work. The hydrazine fuel might have degraded. The valves could have cold-welded shut. Firing them was a massive gamble. If a valve stuck open, the spacecraft would spin out of control and be lost forever. But they had no choice. The commands were written, verified, and sent up through the deep space network, travelling at the speed of light for over 19 hours to reach the distant probe. Then the engineers waited 19 hours for the response. When the telemetry finally locked in on the screens at JPL, the room erupted in cheers. The backup thrusters had fired perfectly. After nearly 4 decades of sleep, the tiny engines awakened and expertly rotated the spacecraft, locking the antenna back onto its tiny blue target. It was an engineering miracle, a testament to the unparalleled genius and foresight of the men and women who built these machines back in the 1970s. Despite these brilliant heroics, the laws of physics are absolute. The plutonium will eventually run out. The engineers estimate that they can keep at least one scientific instrument running on each spacecraft until perhaps the late 2020s, or possibly even the early 2030s if they are incredibly lucky. But the day is coming, very soon, when there will simply not be enough wattage to power the radio transmitters. When that day arrives, the faint, digital heartbeat that has pulsed across the solar system for half a century will abruptly stop. The screens will go blank, the Voyagers will go silent, but the silence does not mean the end of the journey. In fact, in terms of sheer distance and time, the journey has barely begun. The Voyagers are currently moving at over 38,000 miles per hour, essentially falling outward into the galaxy. They have crossed the heliopause, escaping the solar wind, but they have not actually escaped solar system. The true gravitational boundary of our Sun extends incredibly far into the dark. It is defined by the Oort Cloud, a massive spherical shell of trillions of dormant comets and icy debris that slowly orbits the Sun at distances so vast they boggle the mind. The Voyagers, despite travelling for almost 50 years at hypervelocity, have not even reached the inner edge of the Oort Cloud. It will take them another 300 years just to enter it, and it will take them roughly 30,000 years to fly through it, and finally truly escape the gravitational grip of the Sun. Once they are free from the Oort Cloud, they will spend eternity drifting through the Milky Way. They will outlive the engineers who built them. They will outlive everyone currently alive on Earth. They will likely outlive the Earth itself, coasting silently through the vacuum long after our Sun has expanded into a red giant and swallowed our home planet. In about 40,000 years, Voyager 1 will drift within a relatively close 1.6 light-years of a star in the constellation Camelopardalis, known as Gliese 445. Around that same time, Voyager 2 will pass relatively close to Ross 248. In nearly 300,000 years, Voyager 2 will silently glide past Sirius, the brightest star in our night sky. They will become ghost ships, silent frozen artifacts of a civilization that once looked up at the stars and dared to reach out, but tucked safely away inside their cold, aluminum bodies, bolted to their sides, the golden records will wait. Covered in a protective layer of pure gold, shielded from the micrometeorites and cosmic dust, those records are effectively immortal. They hold a billion-year warranty. Perhaps millions of years from now, long after the memory of humanity has faded from the universe, something might find one of these silent wanderers. A robotic scout from another star system, or an advanced biological intelligence, might carefully retrieve the craft, decode the strange etched symbols on the golden cover, and place a needle in the groove. And in that moment, across an unimaginable gulf of time and space, a dead world will speak. They will hear the thunder of our oceans. They will hear the laughter of our children. They will hear the desperate, beautiful longing of a blues guitar, and a simple, hopeful greeting spoken in dozens of forgotten tongues. The Voyagers began as a scientific expedition to photograph the giant planets of our solar system. But they became something infinitely more important. They are the ultimate expression of human hope. They are the realization that while our time in this universe is fleeting, and our pale blue dot is fragile and small, our desire to be known, to explore, and to reach into the dark is eternal. While the physical journey of the Voyager spacecraft is a marvel of orbital mechanics and nuclear endurance, there is an equally fascinating and deeply complex story about how we actually communicate with a machine that is currently drifting over 15 billion miles away. It is a question that often baffles the human mind. How is it physically possible to receive a data transmission, a fragile whisper of radio waves, from a device that is essentially operating on the power of a standard refrigerator light bulb, across a distance so vast that it takes light itself almost 24 hours just to cross it one way? The answer lies not on the spacecraft, but back here on Earth, in an extraordinary planet-spanning web of technology known as the Deep Space Network. When Voyager 1 beams a signal back toward Earth, it uses a high-gain antenna that is roughly 12 feet in diameter. The transmitter pushing that signal operates at about 22 watts of power. By the time that 22-watt radio wave travels across the immense, expanding void of the solar system, passing the orbits of Jupiter, Saturn, Uranus, and Neptune, it spreads out and dissipates. By the time it finally washes over the Earth, the signal is incomprehensibly weak. To put it into perspective, the radio signal from Voyager that reaches our planet is approximately 20 billion times weaker than the power required to run a digital wristwatch. It is a signal so faint that it is constantly threatened to be entirely drowned out by the natural background noise of the universe, the cosmic microwave background radiation left over from the Big Bang, and the ambient electronic hum of our own modern civilization. To catch this microscopic whisper, NASA relies on the Deep Space Network, a collection of massive, highly sensitive radio telescopes strategically placed in 3 specific locations around the globe. There is a facility located in the high desert of Goldstone, California. Another is situated in a valley outside of Madrid, Spain. And the third is nestled in the hills near Canberra, Australia. These three locations were not chosen by accident. They are spaced roughly 120 degrees apart in longitude. This is a brilliant, necessary geographical design. Because the Earth is constantly rotating on its axis, a single radio dish can only point at a distant spacecraft for a few hours before the curvature of the Earth blocks the line of sight. By placing three massive facilities evenly around the globe, NASA ensures that as the spacecraft sets below the horizon at one facility, it is simultaneously rising above the horizon at the next one. It essentially hands off the signal, creating a continuous, uninterrupted, 24-hour line of communication with the darkest reaches of space. The technology utilized at these facilities borders on science fiction. The crown jewels of the Deep Space Network are the massive 70-meter antennas. These dishes are larger than a football field and weigh millions of pounds, yet they are balanced so perfectly on a film of pressurized oil that they can be rotated by a motor roughly the size of a lawnmower. But capturing a signal from Voyager requires more than just a giant piece of curved metal. The real magic happens inside the receivers. Because the signal from Voyager is so incredibly faint, any thermal noise, even the heat generated by the electronic components of the receiver itself, would completely overwhelm the data. To solve this, the amplifiers inside these massive antennas are cryogenically cooled. They are submerged in liquid helium, bringing their internal temperature down to just a few degrees above absolute zero. This extreme deep freeze slows down the random movement of electrons in the metal, stripping away the electronic static and allowing the whisper from the outer solar system to be heard clearly against the silence. But even with cryogenically cooled receivers and antennas the size of stadiums, passing the data is a monumentally slow and painstaking process. Because the signal is so weak, Voyager can only transmit data at an incredibly slow rate. When it was flying past Jupiter, it could send back stunning high-resolution photographs at roughly 115,000 bits per second. Today, from the depths of the interstellar medium, that transmission rate has slowed to a crawling 160 bits per second. It takes agonizingly long periods just to download a single small package of telemetry. And yet, this slow, steady drip of data is precisely what is rewriting our understanding of the galaxy. It is a testament to the fact that the Voyager mission is not just a triumph of the spacecraft itself, but a triumph of the terrestrial listeners, the engineers and technicians who sit in quiet control rooms on Earth, straining to hear the faint digital heartbeat of a machine that left home before many of them were even born. The story of that machine leaving home brings us back to a profound controversy surrounding the Golden Record, the billion-year time capsule bolted to the side of the probes. The popular narrative of the Golden Record is one of unity and scientific poetry, but the actual process of creating it was fraught with intense philosophical debates, legal battles, and a frantic race against the clock. Carl Sagan and his small committee were given only a few short months to somehow summarize the entirety of the human experience, the sum of all human knowledge, art, and biology, onto a piece of copper that would fit in a grocery bag. One of the most intense debates revolved around what images to include to explain human biology and reproduction. The committee recognized that if an alien intelligence were to find this record, they would likely be intensely curious about our physical forms and how we create new life. To communicate this, they commissioned simple, elegant line drawings of a naked human man and woman, specifically showing the woman pregnant, along with diagrams of human conception. But when NASA management reviewed the proposed images, panic ensued. We must remember that this was 1977. NASA was a highly scrutinized government agency, reliant on public funding and the approval of politicians. The idea of sending quote-unquote smut into space, effectively spending taxpayer dollars on interstellar pornography, was a public relations nightmare they were not willing to risk. NASA explicitly vetoed the inclusion of the nude human figures. Sagan was furious, arguing that censorship had no place in a scientific message to the cosmos. But the deadline was looming, and the committee was forced to compromise. Instead of the anatomical drawings, they included a stylized, almost abstract silhouette of a male and female figure, entirely devoid of anatomical detail. It was a stark reminder that even as humanity attempted to speak to the stars, we were still bound by the petty, puritanical politics of our own era. The musical selection process was equally chaotic, hindered by the very earthly constraint of copyright law. The committee desperately wanted to include the song Here Comes the Sun by the Beatles. It was a thematic masterpiece, a beautiful, optimistic piece of modern culture. The Beatles themselves were reportedly thrilled by the idea of their music leaving the solar system. However, the band did not actually own the copyright to their own song. The rights were held by the record label, EMI. When the Voyager team contacted EMI for permission, the corporation demanded a hefty licensing fee. NASA, operating on a strict budget for the mission, refused to pay to send a song into the interstellar void. As a result, one of the most iconic pieces of 20th century music was left off the record entirely, blocked from immortality by terrestrial corporate greed. Despite these setbacks, the final composition of the Golden Record is a breathtaking achievement. It is a deeply emotional, highly curated love letter to a planet that we are slowly destroying. It forces us to confront a terrifying and beautiful reality. The Earth is temporary. Continents will shift, oceans will boil away, and eventually our sun will expand and incinerate our home. All of our monuments, our libraries, our wars, and our achievements will be reduced to elemental dust. But high above the galactic plane, far beyond the reach of the dying sun, the golden records will survive. They will outlast the pyramids. They will outlast the mountains. Long after the very concept of humanity has faded from the memory of the universe, a piece of our music, a photograph of a smiling child, and the sound of a heartbeat will still exist, coasting silently through the dark. The Voyagers are our bid for eternity. To truly grasp the significance of what the Voyagers are experiencing right now, we must deeply examine the terrifying and violent environment they have entered. When we look up at the night sky from the safety of Earth, the space between the stars appears to be a calm, empty, and silent void. It is a beautiful, static painting of pinpricks of light, but the data pouring in from Voyager 1 and Voyager 2 has definitively shattered that illusion. The interstellar medium, the vast expanse between the solar systems of our galaxy, is not empty. It is a highly pressurized, fiercely radioactive ocean of plasma, dust, and magnetic violence, and our solar system is actively sailing through it like a ship navigating a stormy sea. The specific region of the Milky Way that our Sun is currently traversing is known to astrophysicists as the local interstellar cloud. It is sometimes casually referred to by astronomers as the local fluff, but do not let the soft name deceive you. This cloud is a wispy, sprawling nebula roughly 30 light-years across, composed of ionized hydrogen and helium atoms. But where did this cloud come from? The answer requires us to look back millions of years into the violent history of our galactic neighborhood. Scientists believe that roughly 10 to 20 million years ago, a cluster of massive stars located relatively close to our solar system reached the end of their brief, violent lives. These massive stars died in spectacular fashion, detonating in a series of colossal supernova explosions. These supernovas were so unimaginably powerful that their shock waves acted like a cosmic snowplow, sweeping away the dense interstellar gas and dust, and carving out a massive empty cavity in this arm of the Milky Way galaxy. This empty cavity is known as the local bubble, and it stretches for hundreds of light years. Our Sun, carrying the Earth and all the planets with it, is currently drifting directly through the centre of this ancient excavated bubble. The local fluff, the specific cloud we are moving through right now, is likely a remnant, a wisp of shredded material left over from those ancient titanic explosions. Because we are floating inside this local bubble, the space around our solar system is actually much less dense than the average interstellar medium found throughout the rest of the galaxy. We are existing in a relatively quiet, low-pressure pocket of the Milky Way. This is an incredibly fortunate, perhaps even essential, coincidence for the evolution and survival of complex life on Earth. But even in this quiet pocket, the environment is lethal. The primary threat lurking in the interstellar ocean is galactic cosmic radiation. Galactic cosmic rays are not rays of light. They are physical pieces of matter. They are the shattered atomic cores of ancient dead stars. These atomic nuclei, primarily protons but occasionally heavier elements like carbon, oxygen, and iron, have been accelerated by the shock waves of those long-ago supernovas to speeds approaching the absolute speed of light. They are essentially microscopic bullets carrying an incomprehensible amount of kinetic energy. The space outside our solar system is completely saturated with this high-energy shrapnel. A continuous heavy rainfall of lethal radiation moving from every direction at once. If the Earth were directly exposed to the raw, unfiltered barrage of galactic cosmic rays, the consequences would be catastrophic. These high-energy particles would easily pierce our atmosphere. They act as ionizing radiation, meaning they possess enough energy to literally rip electrons away from atoms. If a cosmic ray strikes a living organism, it can smash directly through the delicate double helix of a DNA molecule, shattering the genetic code. Over time, this intense radiation would cause massive cellular damage, rampant mutations, and likely sterilize the surface of the planet entirely. It would also drastically alter our atmosphere, stripping away the ozone layer and altering global cloud formation, plunging the world into a chaotic, uninhabitable climate. The reason we are alive, the reason complex biological ecosystems can thrive on the surface of our pale blue dot, is entirely due to the invisible shield that Voyager spent 3 decades trying to find. The heliosphere. As the Sun blasts out its own localized hurricane of plasma, known as the solar wind, it pushes outward in all directions, creating a massive pressurized bubble that inflates into the interstellar medium. This bubble acts as a cosmic deflector shield. When those lethal high-energy cosmic rays come screaming in from the deep galaxy, they slam into the magnetic fields of the heliosphere. The vast majority of these deadly particles are deflected, scattered, and pushed away, prevented from ever entering the inner solar system. The heliosphere blocks roughly 70% of the most dangerous galactic cosmic radiation from ever reaching Earth. But the data from Voyager has revealed a terrifying nuance to this protective shield. The heliosphere is not a rigid, fixed barrier. It is alive, it breathes. It expands and contracts based on the temperamental moods of the Sun. Our star goes through a natural 11-year cycle of activity. During the solar maximum, when the Sun is highly active and covered in dark sunspots, it blasts out a massive, powerful solar wind. This intense outward pressure causes the heliosphere to inflate, pushing the boundary line further out into interstellar space, creating a thicker, stronger shield against cosmic rays. But during the solar minimum, the Sun quiets down. The solar wind becomes sluggish and weak. Consequently, the crushing weight of the interstellar ocean pushes back, causing our protective bubble to shrink, deflating inward, and allowing a higher concentration of deadly cosmic rays to leak into the solar system. By pushing their sensors directly through this boundary line, the Voyagers provided the very first direct measurements of this dynamic, shifting battle between our star and the galaxy. They proved that our safety in the cosmos is not guaranteed. We are highly dependent on the delicate, invisible equilibrium between the outward breath of the Sun and the crushing weight of the interstellar void. And this realization carries profound implications for the deep future of our planet. As our solar system continues its 250 million year orbit around the center of the Milky Way, we will not always remain in the quiet, low-density pocket of the local bubble. Eventually, millions of years from now, our Sun will drift out of this cleared-out cavity and plunge into a much denser, more violent region of interstellar space. Perhaps a massive molecular cloud where new stars are actively forming. When that happens, the pressure of the interstellar medium will drastically increase. It could become so intense that it overwhelms the solar wind, crushing the heliosphere inward. If the boundary line is pushed close enough to the Earth, we would be fully exposed to the harsh, raw radiation of the galaxy. It is entirely possible that the rise and fall of ancient ice ages, and perhaps even some of the great mass extinction events deep in Earth's geological past, were triggered by our solar system sailing through hostile patches of the interstellar ocean, temporarily losing our protective shield. The Voyagers are not just exploring the edge of the solar system, they are scouting the shoreline of a vast, dangerous ocean that dictates the long-term survival of our entire world. They have shown us that we are sailors on a tiny, fragile raft, completely at the mercy of cosmic currents we are only just beginning to comprehend. And as the twin probes drift further away, their internal power sources fading, their data streams becoming weaker, they leave behind a legacy that will challenge astrophysicists for generations to come. They have fundamentally answered the question of where we are. But the deeper, more terrifying question they have raised is, what happens to us when the cosmic weather changes? To fully appreciate the sheer miracle of the Voyager mission's longevity, it is essential to strip away the romance of the interstellar journey and look closely at the cold, hard engineering of the machines themselves. We are accustomed to modern technology becoming obsolete within a few short years. The smartphones in our pockets, possessing millions of times more processing power than the Voyager computers, inevitably degrade, their batteries fail, and their screens shatter. Yet, out in the punishing, absolute zero vacuum of interstellar space, two machines built during the era of rotary telephones and 8-track tapes are still diligently performing complex astrophysics. How is this physically possible? The answer lies in a philosophy of engineering that prioritized redundancy, simplicity, and brute force durability over sleekness and processing speed. Let us examine the sensory organs of the spacecraft, specifically the cameras that provided humanity with our first close-up looks at the outer planets. Today we capture images using digital sensors, arrays of millions of microscopic pixels that instantly convert light into digital data. The Voyagers had no such technology. They relied on television tubes known as vidicons. These were essentially modified versions of the heavy glass vacuum tubes used in early bulky television sets. When a Voyager camera took a picture, the light from Jupiter or Saturn entered the lens and struck a photosensitive plate inside the vacuum tube, creating a static electrical charge that mapped the image. An electron beam then meticulously scanned back and forth across this plate, line by excruciating line, reading the electrical charges and converting them into an analog signal. Because the spacecraft were moving at tens of thousands of miles per hour, taking a clear picture in the dim light of the outer solar system was a monumental challenge. The cameras had to track their targets perfectly to avoid blurring. To achieve this, the entire spacecraft, not just the camera mount, had to smoothly rotate to keep the lens locked on. This required the precise firing of tiny attitude control thrusters. These thrusters are not massive rocket engines. They are microscopic valves that release tiny, brief puffs of hydrazine gas. In the vacuum of space, a puff of gas with the force of a gentle human exhale is enough to slowly rotate a spacecraft weighing nearly a ton. The precision required is staggering. Over the course of their decades-long journey, these tiny valves have fired millions of times, yet they continue to operate without jamming. A testament to the flawless machining of the aerospace engineers who built them by hand in the 1970s. But once the vidicon tube captured the image and converted it into a signal, there was another massive hurdle. Because the transmission rate back to Earth was so incredibly slow, the spacecraft could not beam the data back in real time. It had to store the information on board and slowly transmit it later. Today, we use solid-state flash memory to store gigabytes of data on a chip the size of a fingernail. The Voyagers had to rely on a mechanical digital tape recorder. It is a physical spool containing hundreds of feet of magnetic tape. Every time Voyager took a picture or recorded a burst of plasma data, electric motors had to physically spool the tape back and forth, writing and reading the magnetic information. Think about the mechanical stress this entails. In an environment where the ambient temperature is hundreds of degrees below zero, the lubricants inside those tape recorder motors should have frozen solid decades ago. The magnetic tape itself, subjected to the harsh radiation of Jupiter and the deep freeze of the interstellar void, should have turned brittle and shattered into dust. Yet, through clever thermal engineering and the strategic use of tiny electric heaters, those tape recorders operated flawlessly for decades. The Voyager 1 tape recorder was finally turned off permanently only a few years ago, not because it broke, but simply because the spacecraft no longer had the electrical power to run the motors. It is a mechanical achievement that defies the planned obsolescence of our modern world. The brains controlling all of this mechanical choreography are three highly specialized computer systems, completely separate from one another, to prevent a single failure from destroying the mission. There is the computer command subsystem, which handles the main scheduling and the interpretation of commands sent from Earth. There is the flight data subsystem, which collects the science data from the instruments and formats it for transmission. And perhaps most importantly, there is the attitude and articulation control subsystem, the inner ear of the spacecraft, which constantly monitors its orientation in the void using star trackers and sun sensors, ensuring the main antenna remains pointed exactly at the Earth. These computers operate at a clock speed of roughly 250 kHz. To put that into perspective, the average modern computer operates at a speed several thousand times faster than that. They do not have operating systems like Windows or Mac. The code is entirely bespoke, written in ancient assembly language, directly into the hardware memory. When engineers on Earth need to update the software to deal with a failing component, or change how the data is compressed, they cannot simply upload a patch. They have to painstakingly write the new code on Earth, run it through simulators to ensure it will not crash the primitive system, and then beam it up, waiting roughly 40 hours for the round-trip signal to confirm the patch was successful. It is the most extreme form of remote tech support in human history. This robust, decentralized architecture is the secret to their survival. The Voyagers were programmed with an extensive library of fault protection routines. If a sensor detects a sudden spike in radiation or a drop in voltage from the nuclear battery, the computer does not wait for instructions from Earth. It immediately executes a pre-programmed sequence. It shuts down non-essential systems, switches to redundant backup hardware, and places the spacecraft into a safe mode, quietly waiting for human intervention. It is this rudimentary instinct for self-preservation, written in thousands of lines of ancient code, that allowed the probes to survive the brutal radiation belts of Jupiter, the freezing shadows of Uranus, and the violent shockwaves of the heliopause. They are arguably the most successful autonomous robots ever created, enduring an environment specifically designed to destroy them, and operating far past their warranty, deep in the absolute silence of the interstellar night. As the power supply on the Voyagers continues its slow, inevitable decline, humanity is being forced to confront a deeply emotional milestone. Within the next decade, perhaps sooner, the final scientific instruments will be shut down. The last watts of electricity generated by the decaying plutonium will be redirected to the radio transmitters, and then, eventually, those too will fall silent. The screens at the Jet Propulsion Laboratory will no longer register the faint, comforting spike of telemetry. The active mission will end. But the end of the data stream does not signify the end of the Voyager's purpose. In fact, their silence marks the beginning of their true eternal mission. They will transition from active scientific probes into something far more profound. They will become monuments, ghost ships carrying the memory of a world that will, inevitably, cease to exist. To understand the ultimate fate of these machines, we must radically adjust our perspective of time. Human history, from the construction of the first cities in Mesopotamia to the launch of the rockets that carried the Voyagers into space, spans a mere few thousand years. In the grand cosmic calendar, this is less than a blink of an eye. The Voyagers force us to think in terms of deep time, in millions and billions of years. Once they go silent, their physical journey through the Milky Way will continue uninterrupted, governed entirely by inertia and the gravitational pulls of distant stars. Because space is essentially a vacuum, there is virtually no friction to slow them down. Barring a highly improbable direct collision with a stray asteroid or a rogue planet, they will continue to coast outward at nearly 40,000 miles per hour for eternity. Let us map their future across the epochs. Right now, they have barely scratched the surface of the interstellar medium. It will take them roughly 300 years just to reach the inner edge of the Oort Cloud, the massive spherical shell of dormant frozen comets that surrounds our solar system. The Oort Cloud is so unfathomably thick that it will take the silent probes roughly 30,000 years just to pass through it. By the time they finally emerge from the other side, truly free from the gravitational anchor of our Sun, the Earth they left behind will be unrecognizable. Over 30,000 years, entire civilizations will have risen and fallen, languages will have evolved beyond recognition, and the geographical face of our planet will have shifted. We may be a multi-planetary species, or we may be entirely extinct, victims of our own making, or of some natural cosmic catastrophe. But the Voyagers will still be falling forward. In approximately 40,000 years, Voyager 1 will drift within 1.6 light-years of a faint red dwarf star known as Gliese 445, located in the constellation Camelopardalis. This star is currently racing toward our solar system, and the spacecraft and the star will essentially pass each other in the dark like ships in the night. Around the same epoch, Voyager 2 will pass relatively close to a star called Ross 248. In nearly 300,000 years, Voyager 2 will silently glide past Sirius, the brightest star currently visible in our night sky. But these are just passing encounters. The probes will not be captured by the gravity of these stars. They will simply fly past, continuing their endless orbit around the supermassive black hole at the center of the Milky Way galaxy. They will complete a single orbit around the galaxy every 225 million years. As the millions of years turn into billions, the Voyagers will bear witness to the slow, spectacular death of our own solar system. Roughly 5 billion years from now, our Sun will exhaust its primary hydrogen fuel. The delicate balance between gravity crushing inward and nuclear fusion pushing outward will collapse. The Sun's core will contract, heating up drastically, causing the outer layers to massively expand. The Sun will transform into a bloated, angry red giant. It will swallow the orbits of Mercury and Venus. It will expand until its boiling plasma surface scorches the Earth, boiling away the oceans, melting the continents, and erasing every physical trace that humanity ever existed on this pale blue dot. The birthplace of the Voyagers will be incinerated, reduced to a charred, lifeless cinder, orbiting a dying, shrinking white dwarf star. But out in the deep, cold safety of the galactic spiral arms, the Voyagers will remain. The harsh cosmic rays and microscopic dust of the interstellar medium will slowly pit and erode their aluminum hulls. The gold plating on the records may become scratched and dull, but the physical structure of the probes and the precious information etched into those copper discs will endure. They will outlive the Earth. They will likely outlive the Sun itself. They are essentially immortal. This staggering longevity forces a captivating, almost heartbreaking thought experiment. Will anyone, or anything, ever find them? The universe is vast, and the probes are microscopically small. Finding a dark, silent spacecraft in the expanse of the Milky Way is infinitely more difficult than finding a single specific grain of sand hidden somewhere in the Sahara Desert. The mathematical probability of interception is incredibly close to zero, but it is not absolute zero. Imagine a scenario, perhaps hundreds of millions of years from now. A highly advanced extraterrestrial civilization, possessing technology we cannot even fathom, detects a faint metallic anomaly drifting through their sector of the galaxy. They dispatch a retrieval vessel. They pull the cold, pitted artifact into their sterile, brightly lit cargo bay. They do not know what a human is. They do not know about our wars, our poetry, or the fact that we looked up at the stars with desperate curiosity. But they examine the craft, they find the golden cover bolted to the side. With advanced analytical tools, they easily decipher the mathematical instructions etched onto its surface. They construct a crude stylus, spin the copper disc, and amplify the signal. And suddenly, the absolute silence of their laboratory is shattered by the sounds of a dead world. They hear the rhythmic crashing of an ocean that no longer exists. They hear the calls of whales that have been extinct for an eternity. They hear the panicked, beautiful wailing of a blues guitar, and the sound of a mother whispering a greeting in a language that hasn't been spoken in 1 billion years. In that singular moment, across an unimaginable, terrifying gulf of time and space, humanity achieves the ultimate resurrection. The Voyagers are not just scientific tools. They are the ultimate defiance of mortality. They are the physical embodiment of our refusal to go quietly into the dark. They are proof that for one brief, shining moment in the vast, indifferent history of the cosmos, we were here, we lived, we loved, and we reached out to the stars. To truly understand the audacity of the Voyager program, we must step back and examine the intense geopolitical and scientific landscape in which it was born. The mission did not happen in a vacuum. It was the direct result of a fierce, decades-long competition that pushed human engineering to the absolute limit. In the 1960s and 70s, the Cold War was at its freezing peak, and the theatre of this ideological war had expanded into the cosmos. The Soviet Union and the United States were locked in a desperate race, not just for military supremacy, but for scientific prestige. While the Apollo program successfully secured the moon for the Americans, the robotic exploration of the solar system was a much more heavily contested battleground. The Soviet Union had established a formidable early lead in planetary exploration. Their Venera probes were achieving the impossible, successfully landing on the hellish surface of Venus, transmitting images from a world hot enough to melt lead before being crushed by the immense atmospheric pressure. They were also aggressively targeting Mars. The American scientific community felt an immense pressure to leapfrog the Soviets, to do something so ambitious, so far-reaching, that it would secure American dominance in deep space for a generation. The Grand Tour alignment presented exactly that opportunity. But reaching the outer planets required traversing a region of space that was entirely uncharted and profoundly terrifying. The primary obstacle was the asteroid belt, a vast ring of rocky debris orbiting between Mars and Jupiter. Before the early 1970s, scientists were genuinely terrified of the asteroid belt. Mathematical models suggested it might be so densely packed with microscopic dust and high-speed rocky shrapnel that any spacecraft attempting to fly through it would be sandblasted to pieces within days. Sending a billion-dollar flagship mission like Voyager blindly into this potential meat grinder was an unacceptable risk. NASA needed scouts. They needed to send disposable probes to test the waters, to brave the asteroid belt, and to take the very first measurements of Jupiter's lethal radiation environment. This critical scouting mission fell to two smaller, less complex spacecraft, Pioneer 10 and Pioneer 11. Launched in 1972 and 1973, the Pioneers were the true trailblazers of the deep solar system. They were the first human-made objects to ever cross the orbit of Mars. As the engineers watched the telemetry, waiting for the expected fatal impacts in the asteroid belt, they were shocked by the data. The belt was remarkably empty. The probes sailed through unharmed, proving that the vast distances between the asteroids were far greater than previously feared. The path to the outer giants was clear. When Pioneer 10 arrived at Jupiter, however, the news was not as positive. The probe plunged into the planet's magnetic field, and the radiation environment it encountered was exponentially worse than any theoretical model had predicted. The radiation was so intense that it nearly fried Pioneer's primitive electronics. The data sent back by Pioneer was a glaring warning siren for the Voyager team. Because of the Pioneer data, the engineers at the Jet Propulsion Laboratory were forced to drastically redesign the Voyager's mid-construction, adding massive amounts of heavy radiation shielding to the computers and sensitive instruments, a crucial adjustment that ultimately saved the mission. The Pioneer probes successfully completed their flybys of Jupiter and Saturn, and like the Voyagers, they too achieved escape velocity, becoming humanity's first interstellar emissaries. Pioneer 10 and 11 are currently heading out into the galaxy in opposite directions from the Voyagers. They also carry a message for potential extraterrestrial intelligence, though a much simpler one than the Golden Record. Bolted to the side of the Pioneers are gold anodized aluminum plaques, featuring a drawing of a naked man and woman, along with a map showing the location of the Sun. But as the Pioneers drifted further into the dark, long after their primary missions were over, they presented physicists with a baffling, terrifying mystery that came to be known as the Pioneer Anomaly. In the early 1980s, navigation engineers meticulously tracking the faint radio signals from Pioneer 10 and 11 noticed something wrong. According to the strict absolute laws of Newtonian physics and Einstein's general relativity, the probes should have been coasting outward at a very specific, predictable speed, slowing down ever so slightly as the gravity of the distant Sun gently pulled back on them. But the telemetry showed that both spacecraft were slowing down faster than they should have been. It was an incredibly tiny discrepancy, a microscopic deceleration, but it was definitively there, and it was happening to both probes simultaneously. For nearly 3 decades, the Pioneer anomaly drove the scientific community to the brink of madness. It was a massive, glaring red flag that suggested our fundamental understanding of physics might be flawed. Theorists proposed wild explanations. Was the gravity of the Sun behaving differently at extreme distances? Was the expansion of the universe itself pulling on the probes? Were we witnessing the gravitational effects of invisible dark matter clustered at the edge of the solar system? The mystery spawned hundreds of scientific papers and fierce debates. It wasn't until the year 2012, long after communication with the Pioneers had been permanently lost, that the mystery was finally solved by painstakingly analysing decades of old thermal data. The answer was incredibly mundane, yet a perfect demonstration of the brutal precision of deep space navigation. The deceleration was not caused by new physics or dark matter. It was caused by heat. The radioisotope thermoelectric generators, the nuclear batteries powering the spacecraft, emit a significant amount of waste heat. The engineers discovered that the design of the Pioneer probes caused slightly more of this thermal radiation to bounce off the back of the spacecraft's main antenna, pushing slightly against the forward momentum. It was essentially a microscopic, unintended photon thruster. The force of this heat pushing against the spacecraft was incredibly weak, equivalent to the weight of a single piece of paper resting on your hand. But over the course of billions of miles and decades of travel, it was enough to noticeably alter the trajectory of the machines. The Pioneer anomaly was solved, proving once again that the laws of physics are absolute, and that exploring the deep dark requires an attention to detail that borders on the obsessive. The Pioneers paved the way, took the hits, and allowed the Voyagers to achieve immortality. The legacy of the Voyager mission extends far beyond the realm of orbital mechanics and astrophysics. Perhaps its most profound impact has been in the field of astrobiology, the ongoing search for life beyond the confines of Earth. Before the 1970s, the search for extraterrestrial life was heavily biased toward a very specific Earth-centric model. Scientists operated under the assumption of the Goldilocks zone, the idea that a planet must be at precisely the right distance from its star so that water can exist as a liquid on the surface. Not too hot, not too cold. Under this strict paradigm, the only viable candidate for life in our solar system was Mars. The outer planets, residing in the permanent, freezing twilight far beyond the asteroid belt, were entirely dismissed as dead, frozen rocks, completely inhospitable to any form of biological chemistry. The data returned by the Voyagers violently shattered this narrow perspective and revolutionized our understanding of where life might hide in the cosmos. The revelation began with the breathtaking flyby of Jupiter's moon, Europa. When the Voyager cameras transmitted the first clear images of Europa's cracked, icy surface, planetary geologists realized they were looking at something impossible. The total lack of impact craters meant the surface was extremely young, constantly regenerating itself. The intricate pattern of massive, intersecting ridges strongly resembled the tectonic ice packs found in the frozen Arctic oceans on Earth. Combined with the magnetic data, the conclusion was inescapable. Europa was not a solid block of ice. It possessed a massive global ocean of liquid saltwater churning beneath a frozen crust miles thick. The heat required to keep this ocean liquid so far from the sun was not generated by solar radiation, but by tidal friction, the relentless gravitational squeezing and stretching of the Moon as it orbited Jupiter. This single discovery fundamentally changed the rules of the game. It proved that the energy required to sustain liquid water, the universal solvent necessary for all known biology, does not have to come from a star. It can be generated internally through gravitational mechanics. If Europa possesses liquid water and a rocky seafloor where chemical nutrients can dissolve, it possesses the fundamental ingredients for life. Scientists began to theorize the existence of hydrothermal vents at the bottom of Europa's dark ocean, similar to the volcanic vents discovered deep in Earth's oceans, where entire ecosystems of bizarre blind creatures thrive in absolute darkness, feeding off chemical energy rather than sunlight. Because of Voyager, Europa instantly transformed from a boring ball of ice into the most promising candidate for finding alien life in our solar neighborhood. But Europa was not the only paradigm-shifting world discovered by the twin probes. As Voyager 1 executed its sacrificial dive towards Saturn's largest moon, Titan, it peered into an environment that offered a chilling, fascinating glimpse into our own deep past. Titan is unique in the solar system, possessing a thick, opaque atmosphere primarily composed of nitrogen. When Voyager 1's instruments sniffed this hazy atmosphere, they detected a rich, complex soup of organic chemistry. They found methane, ethane, hydrogen cyanide, and a host of other complex hydrocarbons. The upper atmosphere of Titan is essentially a massive chemical factory, constantly churning out the organic building blocks of life. However, because the surface temperature of Titan is a staggering 290 degrees below 0 Fahrenheit, any water on the surface is frozen harder than granite. It is entirely too cold for biology as we know it to function. But astrobiologists realized that Titan is a frozen time capsule. It is a massive planetary laboratory preserving the exact chemical conditions that likely existed on the primordial Earth billions of years ago, right before the spark of life ignited. The sheer abundance of organic material on Titan suggests that the chemical precursors for life are incredibly common throughout the universe. They are not rare, magical ingredients unique to Earth. They are literally raining down from the smoggy skies of a moon a billion miles away. The Voyagers taught us that the outer solar system is not a graveyard. It is a dynamic, active laboratory. It showed us that moons are not just passive rocks. They are complex worlds with subsurface oceans, active volcanism, and atmospheres choking with organic chemistry. By breaking the restrictive chains of the Goldilocks zone, Voyager expanded our search parameters to the stars. When modern astronomers use powerful telescopes to hunt for exoplanets orbiting distant suns, they are no longer just looking for Earth twins. Because of the lessons learned at Europa and Titan, we now know to look for giant gas planets with massive moons. Knowing that the gravity of the giant could provide the heat necessary to sustain an ocean in the dark. The Voyagers did not find life, but they definitively proved that the potential for life is vastly more widespread, more resilient, and more creatively adaptable than we ever dared to imagine. They turned a cold, dead universe into a cosmos teeming with biological potential. While the scientific data regarding subsurface oceans and massive radiation belts reshaped our understanding of physics, the Voyager mission also delivered a profound psychological shock to the human race. This shock did not come from an instrument measuring plasma or a spectrometer analyzing atmospheric gases. It came from a single grainy photograph. To understand the monumental cultural impact of the image known as the pale blue dot, we must examine the intense, years-long struggle required to take it, and the deep philosophical vision of the man who championed it. Carl Sagan understood that science is not merely the accumulation of dry facts and numbers. True science must also provide perspective. It must answer the fundamental question of our place in the universe. By 1989, Voyager 1 had long since completed its planetary encounters. It was billions of miles away, climbing high above the ecliptic plane, the flat disk where the planets orbit the Sun. From this unique vantage point, it was looking down on the entire solar system. Sagan realized this was a mathematically unrepeatable opportunity. He relentlessly petitioned NASA management to command Voyager 1 to turn its cameras completely around and take a final series of photographs, looking back toward the center of the solar system to capture a family portrait of the planets. From a purely operational standpoint, Sagan's request was considered a colossal waste of time and a massive risk to the spacecraft. The engineers at the Jet Propulsion Laboratory were fiercely protective of the aging probe. Turning the spacecraft around meant pointing the delicate, highly sensitive optics of the camera precariously close to the Sun. Even from a distance of 4 billion miles, the glare of the Sun could potentially fry the camera's Vidicon tube, permanently blinding the instrument. Furthermore, the managers argued, there was absolutely zero scientific value to the photograph. They already knew what the Earth and the other planets looked like. The Earth would register as less than a single pixel on the primitive camera sensor. Why expend precious attitude control fuel and take up valuable deep space network tracking time for a meaningless, dangerous photo stunt? For years, the request was flatly denied, but Sagan was incredibly persistent. He escalated his request to the highest levels of NASA administration, arguing passionately that the image was not for the scientists, but for the public who had paid for the mission. He argued that throughout human history, we had suffered from a dangerous illusion of centrality. We believed the universe revolved around us. We believed our planet was vast, robust, and permanent. Sagan knew that seeing our world from the outer edge of the solar system would permanently shatter that illusion. Finally, after immense political pressure and the intervention of the NASA administrator, the engineers relented. In early 1990, the commands were beamed across the void. Voyager 1 halted its outward observation, fired its tiny thrusters, and slowly rotated its massive bulk. Over the course of several hours, it snapped 60 separate frames, carefully avoiding staring directly into the Sun. It took months for the slow trickle of data to transmit those images back to Earth, and weeks for image processors to stitch the mosaic together. When the final image of Earth was released, it was exactly as NASA management had warned. It was scientifically useless. The Earth was merely a fraction of a dot, 0.12 pixels in size, caught entirely by accident in the center of a scattered ray of sunlight reflecting off the camera lens. It was a pale blue dot, suspended in a terrifying expanse of absolute blackness. But philosophically, it was arguably the most important photograph ever taken in the history of human civilization. When Sagan presented the image to the public, he delivered a speech that remains one of the most powerful pieces of scientific poetry ever written. He pointed to that microscopic, fragile pixel and reminded the world that every human being who had ever lived, every supreme leader, every corrupt politician, every young couple in love, every creator and destroyer of civilization had lived out their lives on a mote of dust suspended in a sunbeam. The image arrived at a critical juncture in global history. The Cold War was ending, but the threat of nuclear annihilation still loomed heavy. Simultaneously, the global environmental movement was beginning to realize the severe, long-term damage industrialization was inflicting on the climate. The pale blue dot served as a harsh, undeniable mirror. It visually proved that there is no backup planet. The vastness of space is entirely hostile to biology. There is no benevolent galactic civilization coming to save us from ourselves. The thin, fragile atmosphere clinging to that tiny blue pixel is the only thing standing between humanity and the absolute zero vacuum of the cosmos. The Voyager mission, designed to look outward and conquer the unknown, ultimately gave us the most profound, humbling look inward. It forced us to recognize that our differences, our wars, and our territorial disputes are absurdly petty when viewed from the cosmic perspective. It cemented the realization that we are a single fragile crew riding a tiny rock through an indifferent universe, and that our only true responsibility is to protect that dot, and to protect one another. As we trace the staggering 40-year history of the Voyager mission, from the frantic secret engineering of the early 1970s to the mind-bending plasma physics at the very edge of the solar system today, a singular, overarching truth emerges. The Voyager program is not simply a footnote in the history of space exploration. It is the absolute pinnacle of human curiosity. It is the defining endeavour that transitioned humanity from a planetary species to an interstellar one. When we look at the raw data, the sheer, impossible numbers involved, the story borders on the mythical. We took a machine built of aluminum, copper, and primitive silicon, powered by the decaying heat of a poisonous isotope, and hurled it into the abyss at 38,000 miles per hour. We subjected it to the lethal, searing radiation belts of a failed star. We asked it to navigate the complex gravitational cross-currents of frozen alien moons. We demanded that it thread the needle through the razor-thin rings of Saturn and stare into the supersonic, freezing hurricanes of Neptune, and against all mathematical odds, against the brutal, unforgiving laws of thermodynamics and the hostile vacuum of space, the machines not only survived, they thrived. They performed a symphony of orbital mechanics so precise that it defies comprehension. But the true majesty of the Voyagers lies not in what they saw, but in what they are currently doing. Long after the planetary photographs faded from the headlines, these silent sentinels continued to fall outward in the dark. They became our deep space scouts, marching blindly into the terrifying, raw radiation of the Milky Way galaxy. They found the invisible wall of fire that protects our home. They listened to the eerie low-frequency hum of the interstellar plasma. They felt the crashing waves of solar tsunamis rippling across the void. They provided the definitive proof that our entire solar system is merely a pressurized bubble, a fragile lifeboat floating in an incredibly violent, chaotic cosmic ocean. The men and women of the Jet Propulsion Laboratory who built these machines, many of whom have since passed away, essentially built cathedrals of the modern age. Like the architects of old who laid resurrection of grand stone cathedrals, knowing they would never live to see the spires completed, the Voyager engineers built robots designed to outlive them. They built machines that will outlive the United States, outlive modern human civilization, and outlive the Earth itself. The engineering was so robust, the redundant systems so brilliantly designed, that we are still learning entirely new fields of physics from a pair of 1970s computers operating billions of miles from home. And as the inevitable twilight of the mission approaches, as the plutonium slowly burns out and the radio signals finally drop below the threshold of detection, we are left with a profound sense of awe. The screens will go blank. The daily stream of data that has connected us to the edge of the sun's domain for nearly half a century will abruptly stop, but the journey will not. The twin probes will continue their silent, eternal freefall toward the constellation Camelopardalis and the star Sirius. They will become permanent fixtures of the Milky Way, cold, silent monuments to a brief, beautiful spark of intelligence that once existed on a tiny blue rock. Tucked safely against their sides, the golden records will wait in the freezing dark. They are a message in a bottle cast into the ultimate ocean, a billion-year warranty on human existence. They carry our voices, our music, and our relentless desire to be known. Perhaps they will drift through the void forever, unnoticed and untouched. Or perhaps, in some unimaginable future, long after the sun has swallowed the earth, another civilization will pull a silent, frozen machine from the dark. They will place a needle in the groove of a golden disc, and the universe will echo with the sound of our oceans, the rhythm of our music, and the desperate, beautiful hope of a species that dared to reach into the infinite. The story of Voyager is our story. It is a reminder that we are small, fragile, and utterly alone in a terrifyingly vast universe, but it is also a reminder that we are capable of immense brilliance. We are capable of building machines that can touch the stars. We are capable of looking back at our tiny world and realizing the desperate need to protect it. The Voyagers are the best of us, perfectly preserved in the cold vacuum of space, sailing onward into the great, eternal dark. As we reflect on the majestic sweep of the Voyager mission through deep time and space, it is crucial to pull our focus back to the present moment, back to the fluorescent-lit control rooms of the 2020s. The story of Voyager is not just a historical triumph, it is an active, nail-biting drama unfolding right now. The original engineers who sketched out the trajectories on blackboards and hand-soldered the circuitry in the 1970s have mostly retired or passed away. Today, the mantle of keeping humanity's farthest outposts alive has fallen to a new generation of scientists and programmers. These modern guardians are faced with an unprecedented technical challenge. They are essentially performing forensic computer science, managing an active, billion-dollar spacecraft using documentation and code written half a century ago. Operating the Voyagers today requires a bizarre mix of extreme patience and high-stakes hacking. The modern engineering team cannot simply buy spare parts or consult a modern tech manual. They have to dig through dusty archives, deciphering handwritten engineering notes and studying faded blueprints to understand exactly how the primitive electronics were intended to function. When a problem arises billions of miles away, the solutions are often intensely creative and dangerous. Recently, as the power levels dropped perilously low, the team noticed that voltage fluctuations were threatening to trigger the spacecraft's automated fault protection system, a system that could permanently shut down the vital science instruments to save power. To prevent this automatic death spiral, the engineers had to do the unthinkable. They had to deliberately hack into the spacecraft's most fundamental operating code. They wrote a patch to essentially blind the fault protection system, commanding the ancient computer to ignore the voltage drops and force the science instruments to stay on, even as the power supply starved them. It was a massive gamble, sending a software update to a fragile, failing computer 15 billion miles away. Knowing that a single misplaced line of code could instantly brick the entire spacecraft is a terrifying responsibility. But the command was sent, travelling through the deep space network for nearly a full day. When the confirmation signal finally returned, it was a triumph of modern ingenuity married to vintage hardware. The hack worked. The instruments stayed alive, buying humanity a few more precious years of interstellar data. But even with these brilliant software patches, the engineers are fighting a battle against the fundamental laws of physics that they simply cannot win. The thermal energy from the plutonium is steadily bleeding out into the cold void. To keep the thruster fuel lines from freezing solid, which would instantly end the mission by preventing the spacecraft from pointing its antenna at Earth, the team has had to divert power away from almost everything else. The spacecraft is currently shivering in the dark, barely clinging to life. The engineers estimate that by the late 2020s, they will be forced to begin shutting down the final essential science instruments one by one. First, the cosmic ray subsystem might go dark, then the plasma wave instrument. It will be a slow, agonizing process of turning off the sensors of the machine until nothing is left but the faint, empty carrier signal of the radio transmitter. And eventually, even that will fade into the background noise of the galaxy. Yet, as the active life of the Voyagers draws to a close, their scientific and inspirational legacy is actively fueling the next great leap in human exploration. The data sent back from the heliopause fundamentally altered our understanding of interstellar space, and it immediately sparked demands for a dedicated follow-up mission. Scientists and space agencies around the globe are currently drafting proposals for an interstellar probe. Unlike the Voyagers, which were primarily designed to study the giant planets, and only entered interstellar space by accident, this new concept would be explicitly built to explore the space between the stars. Utilizing advanced propulsion systems, perhaps massive solar sails pushed by high-powered lasers or advanced nuclear electric drives, This new probe would be designed to travel vastly faster than Voyager, reaching the interstellar medium in a fraction of the time, and pushing hundreds of astronomical units deep into the local fluff. These future missions will stand on the shoulders of the twin giants. They will use the maps drawn by Voyager 1 and Voyager 2 to navigate the turbulent magnetic storms at the edge of the solar system. But perhaps more importantly, the Voyager mission has permanently expanded the psychological horizon of the human race. When we look up at the night sky now, we no longer see a distant, unreachable tapestry of stars. We see a destination. We know that the space between those stars is not an empty void, but a complex, dynamic ocean, and we know that we have already built ships capable of sailing it. The Voyagers taught us that we are capable of outlasting our own biological limitations. They prove that human curiosity and engineering can conquer distances and environments that the human body could never survive. They are the ultimate expression of our desire to leave a mark, to ensure that the story of Earth is not simply erased by the inevitable death of our Sun. As long as those two golden records remain bolted to their aluminum frames, coasting silently through the dark, the human story continues. The mission is no longer just about exploring the outer planets. It is about securing our place in eternity.